Hello class, welcome to our General Chemistry 2 class. For this video, we are going to discuss two subtopics. One is solids and the other is phase changes. For the objectives, we will have describe the difference in structure of crystalline and amorphous solids, 2. Interpret the phase diagram of water and carbon dioxide, and 3. Determine and explain the heating and cooling curve of a substance. Let's first define a solid. What is a solid? A solid is a state of matter with definite shape, mass, volume, high density, and whose particles are packed closely together. So we have emphasized in the last videos that solids are different from liquids and gases in such that particles in solids are closely packed together. That's also the reason why it has high density, because of the greater number of particles occupying a given space. So these are the common characteristics or properties of solids when compared to liquids. And solids may be categorized into two. They may be crystalline solids or amorphous or non-crystalline solids. Crystalline solids are those that possess rigid and long-range order and whose particles occupy specific positions. Non-crystalline solids or amorphous solids are those that lack well-defined arrangement and long-range order. The Greek term amorphous is the origin of the word amorphous. This means shapeless. Going back to crystalline solids, these are the examples. We have salt, sulfur, quartz, and amethyst. Amorphous or non-crystalline solids, which may include charcoal, rubber bands, lunch boxes made of plastic, and glass paper weights, of course, made of glass. Going back to crystalline solids, these are characterized with unit cells. A unit cell is defined as the repeating structural unit. So you will see in these diagrams, in letter A, we have the smallest unit, the basic repeating structural unit of a crystalline solid, and in letter B, the repetition of the unit cell in 3 dimensions. We have different types of unit cell. So you will see here the different types of unit cells, starting with the simple cubic cell. Notice the measures of the edges or sides ABC, which are the same in simple cubic cell. We also have similar angles for alpha, beta, and gamma at 90 degrees Celsius. Another is tetrahedral, which have different measure of the C, different from edges A and B, but angles are the same also at 90 degrees. Others include orthorhombic, rhombohedral, triclinic, monoclinic. For the packing spheres, we have the illustrations here. A gives us the top view of the atoms in a simple cubic cell. B, we have the definition, and C, the cross-section of each cell. We have 3 different types of cubic cells. We have the simple cubic cell, or in short, SCC, body-centered cubic, BCC, and face-centered cubic, FCC. Notice the number of atoms in each cubic cell. We have the smallest number of atoms or particles in simple cubic cell and the largest number of atoms in face-centered cubic cell. Notice in each face of a simple cubic there are 4 atoms. In face-centered, in each face there is additional middle atom or atom in the middle. In face-centered, in each face there is additional atom. So in each face there are 5 atoms. In body-centered there are 4 and 1 in the middle of all the 6 faces. In simple cubic there is no central atom or atom in the middle of atoms in each phase. So that gives the simple cubic the smallest number of atoms or particles, and phase center the highest number of atoms. These are the definitions of the atoms in each cubic cell, and these are the cross sections. So notice the number of atoms in the simple cubic cell. We have a total of 8 atoms. In BCC or body centered, we have 8 plus 1 in the middle, we have 9. And in body centered, we have 6 additional in the middle of each phase, so that gives you a total of 14 atoms. Crystalline solids are also characterized with crystal lattice. Crystal lattice is the regular repeating structure of crystalline solids. So again, these are some of the examples. Solid, quartz, we have sugar. Other examples include ice. Ice, as we are aware of, pag tinignan natin under microscopic view, ang ice ay well-patterned ang mga atoms. So that's what happens when water is frozen. Nagkakaroon ng regular pattern yung mga atoms. In fact, pag Christmas, ginagamit siyang decor sa mga malls or even sa mga Christmas decor at home. Okay? Sugar, minerals. So the gems, the minerals that are mined and used for aesthetic purposes. So those are also examples of crystalline solids that are characterized with crystal lattice. We also have metals. Most metals, if not all, are crystalline. Alloys are mixtures of metals. We have salts, so sodium chloride is an example. Carbon in the form of graphite and diamond. Long-range order is another characteristic of crystalline solids. This is the repetition of structural units of a crystalline solid over long atomic distances. Notice here quartz. Some amorphous solids do not have long-range order but may have limited localized order in their structures, like in the case of quartz. Quartz have crystalline structure and amorphous structure. Speaking of amorphous structures, let's have amorphous structures which have random orientation of particles that is similar to the liquids and are sometimes referred to as supercooled liquids. Examples are rubber, glass, and plastics. Take note also that when heated, they soften gradually and tend to melt over a wide range of temperature, resulting from variation in the arrangement of particles in their structures. This causes some parts of the solid to melt ahead of the other parts of the solid. We have different types of crystals, and their general properties are summarized here. We have ionic crystals, which are held strongly by electrostatic attraction. Electrostatic force is the force of attraction between charged particles. Examples of ionic crystals include sodium chloride, so most salts, lithium fluoride, magnesium oxide, calcium carbonate. General properties include they are hard, brittle, with high melting points because of strong intermolecular forces. They are poor conductors of heat and electricity. Another group of crystals are the molecular crystals. Examples are the solid argon, solid carbon dioxide, iodine crystals, solid ice, and sugar. The strong forces holding them together are dispersion forces, dipole-dipole, and hydrogen bonds. General properties include they are soft, they have low melting point. Low melting point because of weaker attraction when compared to ionic. Ionic has strong electrostatic attraction. Molecular have weaker IMF. That's why they have lower melting points than ionic crystals. Another type of crystal is the covalent. Covalent crystals are bonded, of course, by covalent bonds. Examples are diamonds and quartz. General properties, they are hard. So we know that the hardest mineral is diamond. They are hard, they have high melting points. High melting points is due to a rigid arrangement of particles. They are hard to uh, to break the IMF. They are poor conductors of heat and electricity. And the last type of crystal, we have the metallic crystal. Of course, they are binded by or bonded strongly by metallic bonds, the strongest force of attraction. General properties include they are ranging from soft to hard. We have metals that are soft like gold. They also have varying melting points, low to high melting points. They are good conductors of heat and electricity. So among these types of crystals, metallic are the good conductors of heat and electricity. The rest are poor conductors. Also, they are generally hard compared to the other crystals, in exception of course with a diamond from the covalent group of crystal. Some examples of metallic crystals include the metallic elements in the periodic table: magnesium, iron, copper, sodium, and all the rest in your periodic table that are categorized as metallic elements. Moving on, what you see here is what? Yes, it's boiling water, melting ice, and the solid here that seems to be evaporating in layman's term, but actually scientifically it is more appropriately described as subliming. So solid subliming or turning into gas. To recall the arrangement of particles in solids, liquid, and gases, of course, we know that solid particles are closely packed. Liquid particles are having spaces between particles. They are not in close arrangement. And gases are in the widest separation. So among the three, the strongest attraction is in solid because they are well packed, and weaker attraction in gases or in between gas particles. When does water or liquid turns to another phase, or generally when does a sample of matter turn or transform from one phase to another? So we have what we call the phase changes. So you will see in this diagram the summary of the transformations, the different transformations in matter. So again, we have three states of matter. Generally, we have solid, liquid, and gas. We have a total of 6 phase changes. Kumbaga, paras-paras sila. We have 2 reverse processes, another 2 reverse processes, and another 2 reverse processes. Let's start with the solid matter or solid state of matter. When solid transforms to liquid, the process is known as, the phase change is known as melting. The reverse process of melting, that's transforming liquid to solid, is called freezing. Liquid turning to gas, we have vaporization. Gas turning back to liquid is condensation. Balik tayo sa solid. Solid transforming to gas without passing the liquid state is called sublimation. And under certain condition, gaseous matter may transform to solid also without passing the liquid state. So we have the reverse processes: melting, freezing, another vaporization and condensation, and sublimation and deposition. The question is, when does a state of matter or matter change from one state to another? You are correct. Temperature. Temperature explains the phase changes. We have here the heating curve for a pure substance. So what you see here are the temperatures along the y-axis and heat added along the x-axis. So what happens when, let's take water as an example. Commonly used example is water to illustrate the transformation of matter from one state to another. Below 0 degrees Celsius, water is in the solid state, in the form of ice. So solid water called ice is under 0 or below 0 degree Celsius. When does water or solid water in the form of ice, when will ice melt, or when can it melt? First, ice needs to absorb heat energy. That amount of heat energy needed to increase its temperature from negative degrees Celsius to 0 is what we call the latent heat of fusion. So that amount of heat is necessary to increase the temperature from negative to 0 degrees Celsius. And then at 0 degrees Celsius, ice will start to melt. So notice here from point A to B, there's heat absorption. So pumapasok po dito yung latent heat of fusion. The amount of heat necessary for the sample matter, in this case ice, to absorb in order to increase its temperature from certain negative degrees Celsius to 0. Hindi po siya aakyat to 0 degrees Celsius unless mag-absorb ng heat energy yung ice. At that point, at point B, where the temperature is already at 0, ice is expected to start melting. Notice the points B and C. Solid water or ice is turning to liquid. At that point, or at these points, notice temperature is not changing. It remains at 0 degrees Celsius. Take note that during the course of melting or any phase transformation, temperature remains at, let's say in the case of ice, it will remain at 0. Kailan po hihinto na or kailan siya aakyat ng temperature? Once ice has completely melted, saka lang siya mag-start magbago ng temperature. At para magbago yung temperature niya, para tumaas, kailangan ulit niyang mag-absorb ng heat energy. So notice the change in heat absorption across the x-axis. So meron kang increase of heat energy from point C to point D. There's absorption. At these points, nagkakaroon ka rin ng increase in temperature. So you started from point C, that's 0 degrees Celsius. As heat is being absorbed by melted water or melted ice that is already in water, nagkakaroon ka ng rise in temperature to 20, 40, 60, 80 until you reach 100 degrees Celsius. And at this point, your water will stop changing its temperature kasi mag-start na ulit siyang transform into another phase. So that's what I meant when I mentioned about temperature remaining during the course of phase transformation. So pag natutunaw siya, pag nagbe-melt siya, hindi siya nagbabago ng temperature. Pag natunaw na siya, saka lang aakyat yung temperature niya until such time that it will start transforming naman from liquid to gas. And at that point, during evaporation, hindi na ulit aakyat yung temperature niya. Mananatili na ulit siya sa 100 degrees Celsius. And that will continue until all the water molecules have transformed into gaseous form or gaseous state. So after niya mag-transform na completely from liquid to gas, umpisa na ulit aakyat yung temperature niya and it will start again to increase its heat energy absorption. So as you can see in the heating curve. So from point D to E, there's constant temperature of 100 kasi that's the course of evaporation. Pero from E to F, that's transforming or absorb vapor water vapor continuing to absorb heat energy, changing its temperature from 100 to a higher temperature. So that's what how we interpret the heating curve for a pure substance. Another graph is called the phase diagram. The phase diagram shows the states of matter, and the critical point and the triple point. Critical point and the triple point are two important concepts that we need to take note of when considering the transformation of matter from one phase to another. Okay, along the y-axis, you see the you see pressure. Along the x-axis, you have the temperature. So it's a pressure temperature graph, or a simply phase diagram. So you see the three states of matter here. We have the solid, liquid, and gas. Tapos meron kang tatlong lines dito na nagva-vary ng kulay. We have red, blue, and green. So yung boundaries po nila, so from the 0 mark to the triple point is the continuous increase in pressure and temperature. That triple point is the temperature and pressure at which a certain substance coexist as solid, liquid, and gas. So that's the point po wherein the temperature and pressure, wherein at that temperature and pressure, yung three states of that sample of matter coexist. So we call that the triple point. Ito naman pong critical point. So in between, so itong line po from the triple point at yung green na yon, yun naman po yung boundary or demarcation between the solid and the liquid state. From the liquid state to the gaseous state, ang boundary naman po nila ay yung blue. The critical point terminates the transformation of liquid to gas. That's the highest possible temperature that the liquid can exist as liquid. So we call that the critical point. So again, critical temperature is the highest temperature at which a certain substance can exist as a liquid. Kasi beyond that, hindi na siya pwedeng mag-exist as liquid. Magta-transform na siya, whether it likes it or not, to gaseous state. So it will continue to transform to gaseous state. Critical temperature is the minimum pressure that must be applied to bring about liquefaction in the critical temperature. Kaya lagi po silang partner. Okay, let's see here the freezing curve. Freezing curve of a substance. Take note, by the way, that each substance has its own phase diagram. So distinct po ang mga phase diagram ng mga substances. For example, water has its own phase diagram, carbon dioxide has its own phase diagram, sugar has its own phase diagram, and so on and so forth. So for this particular example, general example, freezing curve. So we see here solid transforming to liquid. Anywhere in the green line, equilibrium po exists between melting and freezing. So between these two reverse processes, solid to liquid, liquid to gas, or melting and freezing, anywhere in the green line, equilibrium exists between the two phase changes. On the other hand, between another two reverse processes, evaporation and condensation, that's liquid to vapor and vapor to liquid, in anywhere in the line, blue line, exists naman po equilibrium between vaporization and condensation. What do I mean with equilibrium? Magsing bilis po yung proseso, yung bilis ng evaporation and condensation. So that's what we mean by equilibrium. Both evaporation and condensation, or in the previous slide, freezing and melting exist at same rates. I'll repeat, the critical point is the point that terminates the evaporation or vaporization or transformation of liquid to vapor, that terminates the transformation of liquid to vapor of a certain liquid or substance. Let's take a look at the phase diagram of water and carbon dioxide. Let's have water. We all know that the freezing point of water is similar to its melting point, which is 0. Same with evaporation, boiling point at 100 degrees Celsius, and condensation point at same temperature. So katulad ng sinabi ko kanina, during freezing and melting, hindi nagbabago yung temperature. It remains at 0 degrees Celsius. Same with vaporization, habang nag-transform ang liquid to gas, hindi rin nagbabago yung temperature. Basta during the course of phase transformation, temperature remains the same. Okay? Hanggang sa maubos na yung substance from one phase, nag-transform na completely to another phase, saka lang siya mag-i-increase ulit ng temperature until such time na kailangan niya ulit mag-transform into another state of matter. Same with removal of heat. No? Hindi lang naman yung pagtaas pwede rin yung pagbaba ng temperature to transform, let's say, gas to liquid or liquid to solid. So same thing lang. Hindi lang palaging absorption ng heat ang scenario. Okay. So notice here, at normal conditions 1 atm and 0 degrees Celsius, water is at at 1 atm and 0 degrees Celsius, water is in the solid phase or in the solid state. At 100 degrees Celsius and 1 atm, water is at liquid phase. Okay? Pero in these normal conditions, 1 atm, the physical state of carbon dioxide, let's have 1 atm, it's solid. But if water is solid at 0 degrees Celsius, carbon dioxide is solid not at 0 degrees Celsius but far below 0, which is negative 78. So at normal pressure of 1 atm, carbon dioxide is solid, but at a very low temperature of negative 78. Let's have the liquid state. At 1 atm, at 1 atm and at it can never be possible that carbon dioxide will exist as liquid at same conditions as water that exists in liquid. If water exists as liquid from 1 degree Celsius, for example, ang carbon dioxide ay hindi. It has to reach what? Higher than negative 57 degrees Celsius. Negative 57 degrees Celsius. And at a much higher pressure. Kung ang water requires only 1 atm and above 0 degrees Celsius to become liquid, ang carbon dioxide ay hindi. It requires higher pressure of 5.2 and at least 56 negative 56 degrees Celsius para mag-exist siya as liquid. So under normal condition, carbon dioxide is indeed solid and cannot come in a liquid. That's why carbon dioxide is referred to as dry ice. That's the reason. Look at the critical points. Okay, the critical point again is the point or the temperature and pressure at which the three states of that matter coexist. So the triple point of water is pressure of 0.06 atm and about 0.01 degrees Celsius. While that of carbon dioxide, the critical point is at negative 57 degrees Celsius and 5.2 atm. So at this temperature and pressure, all the three states of carbon dioxide, solid, liquid, and gas coexist. Okay, these are some examples of the substances that have their own critical temperature and critical pressure. As I said, each substance has its own phase diagram. So that will be all for this video. I hope you learned something about solid and phase changes. I hope to see you again next time. Thank you for watching. Until next time.